So in this video, I'm going to explain the next arithmetic instruction, which is called ADI. So the meaning of this ADI is add immediate to accumulator. So here the functionality of this instruction is given in this statement itself, that add the content of accumulator with the 8-bit of the immediate data and store the result into the accumulator itself. So here the opcode for this instruction will be ADI. The opcode for this instruction is ADI, and as a operand it should have only 8-bit data. The reason behind that, accumulator size is 8-bit only, so we can add the similar size of the data together. So that is the reason operand it has taken here as a 8-bit of data. Now we can understand their detailed functionality with the example, and then we'll fill rest of the part here. So for example, if I am writing here ADI 59H, and before execution of this instruction, if this accumulator is having as a 4AH and the data we have here 59H, so now it will perform the addition of these two operand here. So this accumulator content is 4AH. It means in the binary this can be written 0, 1, 0, 0, and for this A means 10. So this will be 1, 0, 1, 0. So this is 4A. Now we are having that 59H as a data here. So this data it is taken here as a 59H. So this can be written in binary form as a 0, 1, 0, 1, and 9 can be written 1, 0, 0, 1. So now we have to perform the addition here. So from the first stage 0 plus 1 it will be 1, then next will be 1 plus 0 it will be 1, third stage 0 plus 0 it will be 0, fourth stage 1 plus 1, so sum will be 0, carry will be 1. So here 1 plus 0 plus 1, so sum will be 0, carry will be 1. So 1 plus 0 plus 0 it will be here 1, and 1 plus 1 sum will be 0, carry will be 1, and at the last stage 1, 0, 0, so this will be 1 here. So now we got the result here as a 1, 0, 1, 0, it is here A, and this 0, 0, 1, 1 means 3. So in the binary this can like 1, 0, 1, 0, 0, 0, 1, 1 can be written in terms of hex as a A3H, and this result will be stored into the accumulator. So now we can see that their impact over the flags also, how their flags is going to be changed. So we will see here as a flags. So as a flags we can write it here sign 0, then auxiliary carry, then parity, then carry flag. So as a result from this last position, if you'll see that their value is 1, so sign bit will be here as a 1, and the result is non-zero. It means all the bit is not producing here 0, so it is non-zero. So that is the reason this 0 flag will be reset here. So this will be 0. And from the fourth stage, it means from this stage that auxiliary carry has generated. So that is the reason this auxiliary carry status will be 1, and the number of ones in this result it is here 4, so it is called even number of ones it is available in the result. So due to that reason it will perform even parity. So under the even parity, this parity bit status will be 1, and there is no carry generated from their MSB side. So that is the reason this carry flag will be 0. So this is the impact after performing this addition, and here this content of the accumulator will be modified as a A3H, and their flags will be modified in this fashion. So here in the note we can write, it here, that all the flags are modified. All the flags are modified as per the result obtained after performing this addition operation by the use of this instruction. Now we can find out their size here. So if you see that their size, how we can find out. So let's say before execution of this instruction, if this instruction is stored at somewhere at our assumed location as a 1000H. So at this 1000H, let's say their opcode will be XXH will be stored first, and at the very next location as a 1001H, this data will be stored 59H. So before execution, this will be stored into the memory, and here first of all we have to look at for their size. So it is occupying two memory locations, so their size will be 2 byte here. Now we will talk about that, their machine cycle. So by default for any instruction, the first machine cycle will be opcode fetch. So and the second machine cycle will have here that reading of this data, reading of the operand as a data from the memory. So for execution of this instruction, this microprocessor is accessing memory chip two times. Once to read their opcode, and the second machine cycle will be treated here as a memory read, because this 59H is coming as an operand from memory to the processor, because it is the immediate data here. So this cannot be stored inside the processor, it is outside of the processor, and this can be accessed from the memory. So it is accessing two times of this memory chip. So that is the reason their machine cycle will be 2 here, and the first operation is called it here as a opcode fetch, and the second operation is called as a memory read. And as we know that for the opcode fetch, by default it is required 4 T state, and for the memory read it is required 3 T state. So total number of T states required for the execution of this instruction is 7 T states. So I hope you understand this instruction in the better way. Thank you.